All right, good. So what we were doing last time is we were doing the sigma model. And we had done the scattering amplitudes. We had done pi plus goes to pi 0, scatters. They exchange a sigma, and then there's this contact interaction. And there's this big cancellation going on, and the matrix element turns into I q squared over v squared 1 plus q squared over lambda v squared is what it is. Is that right? Let's get it right. Back here. 2. There's a 2 there, sorry. Plus dot dot dot. Yes. And we wrote an effective Lagrangian for the first piece. This had a lot of different forms, but it could be an effective Lagrangian that, for example, starts off as 1 over v squared. It's minus 1 over v squared d mu pi 0, d mu pi 0, pi plus pi minus. That gives you that once you take its matrix element. What I didn't quite get time to do is we can do one for that too. The effective Lagrangian for that could be, let's call it L4 because there's 4 derivatives. Could be d mu pi 0, d mu pi 0, d sigma pi plus, d sigma pi minus. And the coefficient is 2 over v squared m sigma squared. And that can be written in various ways. It's, 1 over lambda v to the 4th, dot, 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 dot. There's a bunch of things. Actually, knowing this actually is useful because it's going to end up having that form in a few minutes when I do it another way. Okay, so the 1 over lambda v to the 4th is interesting. I actually find it interesting. I'm not sure why it should be surprising, but here the effective Lagrangian goes like 1 over a coupling constant, 1 over lambda. Okay, v is this maximum expectation value, so there's lambdas in there too, but still, we'll see when we write out the effective Lagrangian that the 1 over lambda is an important piece. Okay, it's sort of unusual. All right, so that was the calculation from last time. This time I'm going to tie together a few things that we've done over the course of the study of the subject. I'm going to change my representation and write it in the same result in a better way, and then get from that the minimal effective Lagrangian. Okay. So what I'm going to go through is this exponential parameterization. Okay, we've been using sigma it was the original sigma plus I tau dot pi, which after shifting the field was v plus sigma twiddle, which was the fluctuation, the quantum field, plus I tau dot pi. And we're here going to define this as v plus f times u, with u, there's a definition, u is e to the I tau dot pi prime over v. Okay, so we've done this a little bit, but let's just remind ourselves what we're doing. This is a change of variables that's in this sense of Hogg's theorem. Hogg's theorem says that you get the same physics as long as the linear terms are the same. So if I expand this, you can see that the linear order S is equal to sigma plus dot dot dot, where dot sigma twiddle dot 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 involves pi prime fields from here, but just if I take the first order piece, they're the same. The pi prime is a little less clear, but it's, if I expand this, so let's write it out here. Right, this is 1 plus I tau dot pi prime over v plus dot dot dot, and then multiply by this, you see that the first term is the same also, so pi I prime is pi I plus dot dot dot. So it's a linear order, they're the same, but then they're not the same after that. But Hawk's theorem says that this should be the same physics. Okay. And our Lagrangian was previously, we had L was, what was it? It was 1/4 trace d mu sigma dagger d mu sigma. Then there was a minus v of sigma dagger sigma. And there was the nucleon piece, which psi bar I d slash psi minus g psi bar sigma left, right plus the Hermitian conjugate. Okay, so that's our Lagrangian, which you guys showed as a homework. Just didn't. In V? Yes. Yes, it should be a trace. Thank you. Yes. Actually, I don't even have to write it. If you look at, let's just look at that. Sigma dagger sigma is V plus S squared U dagger U. Since U dagger U is 1, it's just V plus S squared anyhow. So the trace actually wasn't needed there. We did use that. That's how we wrote it last time, but that was mainly just, in the other representation it's not as obvious. Right? In this representation it's trivial that this doesn't need the trace. In the other representation it seemed to need it. Okay. So what do I want to do here? Well, clearly I want to rewrite that. When I look at the kinetic energy pieces here, those guys, there's going to be terms where there's the traces, the derivatives act on the S, or the derivatives act on the sigmas, or in principle there's cross terms. If I take then trace d mu sigma dagger d mu sigma, that equals, well, when it both act on the S's, it's d mu S trace sigma dagger sigma, which is just 2. I mean U dagger U. Sorry, we got array of U's there. Right? The cross terms look like two, well, d mu S trace U dagger d mu U plus d mu U dagger U, and then there's, I guess, in this term there's 1 V plus S because the one derivative, one of the U's has a derivative on it, but the other doesn't. Okay. And then there's the v plus s squared trace d mu u dagger. Okay. So this first term is trivial. The second term is 0. There's actually, looking at it, there's two ways to show it. One is I just happen to know, and we'll show you later, that each of those terms is separately traceless, so the trace kills it. The other way to see it is that this is the derivative of u dagger u, which is the derivative of 1, which is 0. Okay, so either way, we get it to vanish. So the kinetic energy pieces are going to have this term for the s, this term for the u's. The v is just v plus s, so it only involves s's, no more pi's, so that v, what used to be sigma and pi, now turns into just mu squared over 2 v plus s squared minus lambda over 4 v plus s to the fourth. It comes out of that a mass term. Well, I'll just write out the answer now at this stage, right? So then overall, then the Lagrangian is v plus s squared over 4 trace d mu u dagger d mu u plus 1/2 d mu s I've factored out the mass term. Then there's minus lambda v s cubed minus lambda over 4 s to the fourth. I've dropped the constant, and then the fermion pieces sidebar left u side right plus sidebar right u dagger side left. So that's another way to write the old sigma model Lagrangian here. What's funny about it is that the renormalizability seems to be lost. It's not, but it's hidden. So you certainly would have a hard time knowing how to renormalize that because it has this exponential, so it's technically non-renormalizable. But it's the same theory, so if you tried it, it would work. You just wouldn't know it ahead of time. But the other thing that's also interesting about it is the symmetry is now visible. Okay. Remember when we did the sigma model Lagrangian and you shifted the sigma fields and had the sigma twiddle, you could no longer see that symmetry. The symmetry of the sigma model wasn't obvious anymore. But here it's still there. Now we have a symmetry that takes u goes to L u r dagger. Psi goes to L psi, psi left, psi right, goes to R psi right, where these guys live in SU2. They're SU2 matrices. Okay? Then you can just see it. It's just like before. This is invariant. This is invariant, and nothing else depends on those fields. So the other way was obviously renormalizable, but the symmetry was hidden. This way, the symmetry is hidden and renormalizability is. This way, the symmetry is visible, renormalizability is hidden. But that's what it is. Okay. So now let's do the scattering in this case again. Okay. Well, we're doing the scattering of the pions. So this trace, this one, it's V plus S squared over 4. I'm going to drop the fermions here. The pions then only live in that first term. Okay, so if you drop the fermions to just that first term, we have trace d mu u dagger is, well, it starts off like I have trace of d mu pi over v d mu, that's tau dot pi, tau dot pi over v, plus it turns out there's terms with pi to the fourth, two derivatives and pi to the fourth plus etc. Those are exponential, so they all sit there. So there are interaction terms, which we'll have to try to pull out, that go like 4 pions. There are interaction terms that go like 6 pions. There are interaction terms that go like 2 pi's and an S. There are ones that go like, 4 pi's and an S. Etc. So there's all these terms there. But for what we're doing, we'd expect that the only things you need at tree level, there's this guy plus this guy. Okay, so there's pi, S, pi. Okay. Well, one of the things that you can see from looking at that Lagrangian is that each vertex there has 2 powers of the momentum. So this thing goes like energy to the squared. That vertex up there goes like energy squared. This one down here goes like energy squared. So this is the only one at order q squared. This guy comes in order q to the 4th. Okay, so those are the 2 that we're interested in. But back when we did it the previous time, these both started at order 1. They had a cancellation. Their cancellation ended up being of order q squared. Here, if I want the q squared piece by itself, I don't even need that second diagram. So even the diagrams you consider are different in this case. If I was just doing the q squared calculation, I just need that one term. Okay, so let's do the q squared calculation. So the only thing I need is I need the Lagrangian is v squared over 4 trace d mu u dagger. Okay, so that's of course, this is our effective Lagrangian here. That's the only thing we need to do this. And let me just show you some tricks, just because I know some of you will end up working on this thing. It's useful if you're writing this to write it in the following form: is d mu u dagger d mu u dagger. Okay. So this you'll sometimes see being written as v squared over 4 trace L mu. L mu is this d mu u dagger. And it's the labeling L is just because this thing goes to that left-handed matrix L's on both sides, right? There's an R and an R dagger and an R right in there. They cancel each other out. So this transforms just purely left-handedly. Okay, and you could have used an equivalent right-handed one there, but it doesn't make any real difference. Okay. If I start calculating it, we see that it starts off as I tau dot pi over V plus, minus, minus d mu f let's make my notation tau dot pi over V is equal to phi, just for the moment. So if phi minus 1/2 phi squared, and I take the derivative of that, and then there's minus I over 6 d mu phi cubed, 1 minus I phi minus 1/2 phi squared, etc. Okay, the trick that I just wanted to emphasize is if you do this calculation, this ends up being linear tau I times some left-handed stuff, which I'll work out, but it's proportional to tau. At this stage, it's not obvious. So, for example, here is a tau times 1 term, so that doesn't look like it's linear in tau. And then there's terms way down the line that are tau to some large power. The way it works out that way is, the first term works, of course, by itself as I phi, and that should have been a derivative there. So it's I d mu phi. So that's linear. Let's just work out the next term just to see how it works out. Then I have minus 1/2 phi d mu phi plus d mu phi from that term. And then also at this order here, I have this minus I times that one. So it's plus 1 d mu phi times phi. Okay, and I won't do the next order terms. I have them all written out in my notes, but this then, these two combine up to be plus 1/2 d mu phi times phi minus phi d mu phi. If you write out what that is, that's 1/2 tau I tau j d mu phi I phi j. Right? So this first term here, tau I d mu phi, is the first term. And the second term is it's sitting on the other side of it. So this turns into the, the 2i epsilon ij k tau k. And so this term is also linear in tau. Okay. The terms that sit over here turn into, I'll just write out the answer just so you can see how the pattern starts developing. It's minus I over 6 turns into phi commuted with phi commuted with d mu phi. So this commutator gives a tau. There's another commutator of a tau with a tau. You get a single tau back. So you always have one tau back. So then Li mu is I d mu phi I plus epsilon I j k phi j d mu phi k plus epsilon I j k epsilon k l m phi I phi l d mu phi m plus dot dot dot. And you can sort of get the higher terms from that pattern. Okay. The point of that is it's now just algebra to take that trace. The trace then turns into, up here, it turns into v squared over 2 Li, and it's mu's. There's two mu's too also. Okay. Then you just multiply it out, just a bunch of algebra. When the dust settles, L is 1 over 6 v squared pi dot d mu pi dot d mu pi minus pi dot pi d mu pi d mu pi. Okay, so there's one with the isospin symmetry invisible. That's just gotten by multiplying out. Anybody have any questions on the technical stuff there? Just on how you do it? It's slightly painful, but not too much. If you then write it out, there's a series of terms here. There's, it starts off as 1 over 6v squared. The first terms that you find are, there's minus d mu pi 0 and d mu pi 0 times pi plus pi minus pi plus dot dot dot. So there's a bunch of terms. They all look like this other effect of Lagrangian that we had. They all have the two derivatives. And if you take the matrix element, if I take this matrix element, I'm sorry, I just not that one. It just ends up being, so this is pi plus, pi 0, ends up being I q squared over v squared, just like before. That part's not the surprise, I guess. Okay, but what we've seen is that that you can reproduce the same first order result with L effective equals v squared over 4 trace d mu u dagger. So sigmas have been s's have been removed completely. So that's our effective Lagrangian. The other thing that you could do with this is that this gives all matrix elements. To this order, to order q squared. Okay, so if you wanted to do pi goes to 4 pi's, or other stuff, this would also do that. So you've got the same Lagrangian giving you all these, whereas in the old way, you'd have to do, you'd have diagrams that go like sigma twiddle, but pi there, plus all these other guys. The effect that you'd have there is there'd be lots of cancellations. Because the end result has to be of order q squared, and none of the diagrams start out at order q squared. They all start out constant order. So all these diagrams, I know I didn't do the count, but there's a large number of them, have to all add up in just the right way to cancel. Okay. So the other nice thing about this is that all the pi amplitudes start at orders q squared. Okay. That's not at all obvious in the other way of doing things. And the reason it's obvious here, and this gets into some little hand waving, but it's true, is the symmetry is visible here, and the symmetry forces it. Okay, so let's try to make that argument. Let's wave my hands. Let's imagine going back to this one-dimensional example. This clearly is, 3 pions and a sigma. But let's just imagine there's 1 pion and a sigma. So here's the little original sigma pi direction. Okay. The pion, the ground state's right there. The pion field is this excitation along that direction there. And we argued originally that the pion mass, so the quadratic piece, has to vanish because of the symmetry, and that was Goldstone's theorem. So if you're just moving around that point there, the fact that you move instantaneously to a state of the same energy, so until that curvature becomes big, then it doesn't cost you any energy, so there can't be any m squared pi squared piece, because that would, in the Hamiltonian piece, then that would cost you energy. Does everyone remember that argument, the Goldstone argument? Okay, but now we've enhanced it. This says that all orders in pi, even pi to the fourth, pi to the sixth, pi to the eighth, there's no constant pieces. So we're going to get out of this no pi to the n terms at all. Okay? And that's the symmetry, and it's completely invisible in the original sigma parameterization, but it's visible here because the sigma direction, the symmetry direction, is e to the I tau dot pi over v is in the angular factor. Okay, and that symmetry is still manifest. U goes to L, U R dagger. So the symmetry is still there, but basically these pions here aren't just that direction. They're the ones that they're the angular factor. So if I was trying to draw it, the pi primes which enter into there are the ones that rotate in the symmetry direction exactly. They keep the symmetry. So you can't have any of these terms because all the Hamiltonian for constant values of the field all has the same energy. I don't know how coherent that was, but that's what the argument is the symmetry forces all amplitudes to vanish at zero energy because there's this symmetry ground state there. So it's not just the mass, it's all amplitudes. Okay. Okay, anybody else? Any questions? Okay, so let's then try to formalize this a little bit more. Let's look at the path integral. Okay. And define our effective Lagrangian that way and see that what we're doing is really just that. We have the path integral is given in the full theory by ds d pi e to the I action and we could put a source term here which we couple up to pions. Let's do that. Okay. There's no need to put a source coupled up to the S fields because we're not going to put any of them in the external states. They're too heavy, so we don't produce them at the energies that we're interested in. Okay, but now we integrate out the S. So we write this as integral d pi times the integral df e to the I stuff, the stuff that we have there. And this is then the integral d pi e to the I integral d for x L effective. Now it's only of pi. Okay. So it's earlier we would have called this e to the I w of pi. Okay, so doing that path integral, then we do this path integral, we call this guy here e to the I w pi. It can only depend on pi, and then we parameterize it as an effective Lagrangian. Okay, so that's the technical correspondence. The only subtle point is this locality. Okay. So we have e to the I w of pi from that path integral, and we write that as e to the I integral d for x, some effective Lagrangian. Okay. That step requires that this be local. To a physicist, this is obvious. Okay, this is, so I'll put it in quotes. By the uncertainty principle, once you understand what's in that path integral, it's just all these Feynman diagrams. These Feynman diagrams involve this heavy particle. Heavy particle can't propagate far, so it's obvious. It's actually not as obvious as that, even really to physicists. The math part that's a bit tricky is that these objects are singular. They're pretty singular. And so if you imagine just having two things, we did these things just blindly, but we integrated out things like J propagator J. Well, you put those two J's as quantum operators close to each other, they are somewhat singular, and the tool for this is what's called the operator product expansion. I'm going to do this for you a bit later on, but let me just tell you what it is. Okay, it's basically if you have two things, A of x, B of 0. So one of these could be one of the currents, and the other one could be another current. They don't have to be the same thing. As they get very close to each other, we will end up writing this as sum over a whole bunch of operators, some coefficients that depend on x, and the operators that are evaluated at the origin. Okay. So these guys are going to be functions. Technically, they're called Wilson coefficients. These are local operators. Okay. This turns out to be the math piece that allows us to write this general path integral which are as functions of operators. Remember, we've got all these terms from doing this path integral, but they're going to be evaluated very close to each other as something that's local. This is proved in perturbation theory. Okay, so this expansion in terms of defining a set of local operators is provable in perturbation theory. It's assumed to be true non-perturbatively. There's no counterexamples that I know of. It's certainly it's built into lattice calculations, too. Lattice calculations, which are non-perturbative calculations, show this feature. Okay. But that's the math obstacle to making this work. And the proofs are real math proofs. I mean, this is not ones that are easy to read. Okay. But if we get back to this, then we end up then, for our case, we have e to the I w of pi is the integral ds e to the I integral d4x, well, v squared over 4 plus 2v f over 4 plus s squared over 4, so it's, we didn't have to trace d mu u dagger, plus the kinetic energy plus the, well, I'll write it out, minus lambda v s cubed, and it's lambda over 4 s to the 4th. Okay. Okay. So one of these pieces, of course, is what we just found. If I pull this first term out, doesn't depend on s, it goes outside there. So there's an e to the I integral d for x, v squared over 4, trace d mu u dagger. And then there's the remaining piece, which comes from this guy here, and this guy here, and in principle those guys, right? So I'll just call it e to the I w12. So we've got our first term in our effective Lagrangian. The next term is also pretty obvious. Remember, we've now done this a couple times, so a lot of things are coming together here. Here's a linear term in this. So if we have the kinetic energy piece, the first correction is this linear term, and let's forget the others for the moment. Okay, the linear piece then gets so the next order correction is, you know, we use the integrating out trick. We have schematically we take e to the I integral d for x, s operator s plus j, s times j, and that turns into, after you do the path integral, it turns into some number times e to the I integral d for x, d for y, j propagator j, right? So we've done that a couple of times. So we can in fact write out the next order term also. And so if I just keep, at the moment I'm just keeping these first two guys, we then write out L effective is v squared over 4 trace d mu u dagger plus it's v squared over 8m sigma squared, ms squared, whatever it is, trace d mu u dagger, d mu u, trace d nu u dagger. Okay, so that's the piece that you get from expanding that, and then there are plus higher order terms. Okay, so by doing our integrating out trick, we get the next order term also. And if you apply this, you end up with then the matrix element is the iq squared over v squared. You know, there's 1 plus, it was q squared over 2 lambda v squared. The next order term, dot, dot, dot. Okay, so you reproduce the whole thing. Okay. The coefficient here, remember, ms squared was 2 mu squared, which is 2 lambda v squared. So that factor there, v squared over 8 ms squared, is 1 over 2 lambda. 1 over 16, sorry. Okay, it's strictly just the inverse of the coupling constant. Again, a bit odd, but that's what it is. It's a dimensionless piece. You can sort of see, let's do dimensions quickly. V is dimensions of mass, the derivative is dimensions of mass, so mass to the 4th. 4 derivatives, dimensions of mass, U is dimensionless. So this should be dimensionless there also, so it's just a pure number. Okay, so we've seen the following. We've seen locality, we've seen the energy expansion, we've seen the fact that we end up with a non-renormalizable L effective, and we've seen that the symmetry is, in this case, it's not broken. At least in this effective Lagrangian. So the first 3 are general effective field theory results. The last one is actually a lesson in spontaneous symmetry breaking. Remember the phrase spontaneous symmetry breaking, B stands for breaking. And this sigma model is an example of a symmetry breaking, but it's really not broken. There it is. You can see it there. It really is hidden. And in fact, this particular trick, we don't even hide it. It's visible. So the general lesson is the symmetry still is there. It just is sometimes hidden. Okay. Any questions about what we've done there? The next thing I want to do is transition to a discussion of loops. So let's come back up here. Think about the other terms in this Lagrangian here. This s squared piece here, the s cubed s to the 4th. These guys, the s squared piece in particular, would lead to a vertex So if we had s squared trace d mu u dagger, there'd be some diagram that has pions coming in, some number of pions coming in, and then s, there's some matrix element from that, which if you apply it twice, goes like that. So there are certainly diagrams where S runs in loops. And so we need to also then do loops somehow in this framework. Okay? And I'm going to try to do it somewhat explicitly here in what I'm doing. Certainly not today, though. Okay, but what's going to happen in this section is that we're going to bring up the idea of matching. Okay. Matching is a code word for a technique in effective field theory. It's especially true when you have a case like we have here. The sigma model is a renormalizable theory. So if you treat it right, all predictions are in terms of two parameters, lambda and m sigma, for example. If you know those, then you know all the predictions of the theory. That's all you need there. Or you could make it v. We could change that guy to v squared if we want. The effective theory is not renormalizable. Well, it's non-renormalizable, really. Yet we'll do the calculations there, but the non-renormalizable says that there's many parameters in principle. Okay. Matching is then just the technique is to take the parameters of the effective theory and match them to the parameters of the full theory to determine what your parameters are in your effective theory. We did this already at tree level, but it's especially interesting, in loops. So we do it order by order. Okay. So that's going to be our goal. Yeah. Why don't I stop here? I know it's a little early, but it makes for a more logical presentation next time. So what I'm going to do is I'm going to start off by defining my effective theory more fully than I've done so far. I'll do a calculation in the effective theory, a one-loop calculation. I'll do a one-loop calculation in the renormalizable theory. I'll show you that they have many features the same. And then if we choose these parameters they're exactly the same to a certain order. Okay, so we'll do the whole matching. I think it probably takes much of the next time. Okay. Good. So let's stop there and come back and do that next time. Okay. Good. Any questions before we go? Yes.
Now, X there.
Yeah.
So, what do you mean by same physics?
It means that all scattering amplitudes are the same. Okay. Now, it clearly didn't mean that all Feynman diagrams that we should consider are the same. but the Feynman diagram is not a scattering amplitude. So if you take, physical external states and look at some S matrix element, those are guaranteed to be the same by Hogg's theorem, but everything else in the middle isn't. So that's the content. Okay? And technically it says only on-shell external states. So if you get a matrix element with, you write some matrix element there with pions or nucleons or something. But sometimes you take a matrix element and you pretend that the external states are off-shell. Hogg's theorem doesn't say that those are the same. Okay? It only says that when they're on-shell, it's the same. And it's actually funny to watch it. When you do these calculations, you can see the equivalence on-shell and the inequivalence off-shell of these. It's one of the things that if you do it enough times, you start realizing that off-shell matrix elements really are ill-defined. And there's debates in the journals about, these two things are equivalent on-shell but inequivalent off-shell. But since we're doing scattering processes, they're sometimes off-shell, so they're really inequivalent. That's bullshit. It's not. It doesn't how it works out at all. So there's a lot of really lousy arguments out there in the literature that just are very naive about some of these things. A very big one is the pseudoscalar versus pseudo-vector coupling for pions. If you're doing pion theories now, you'll see this. You can couple pions by psi bar tau dot pi gamma 5 psi, or you can couple it as psi bar gamma mu gamma 5 d mu pi, so a derivative coupling. If you take those matrix elements on shell, they're the same. But there's this enormous literature about how they're inequivalent off shell. It's nonsense literature. It drives me batty. But to be fair, this wasn't always obvious. Back in the early days of field theory, people did have these debates because you do some little bitty calculation and it seemed to give a different answer because you're doing some approximation. Your approximation just wasn't complete. And so people got into it, but they didn't understand field theory back then. And then one of the advantages of having gone through all this development of effective field theory, especially in, let's say, nuclear physics, where the field as a whole transitioned from sort of quantum mechanics treatments, non-field theoretic based to field theoretic based. In that transition, there were a lot of these arguments that just weren't very accurate. It becomes much more obvious when you use the effective field theory treatments for nuclear physics how it should work out. So, my rant of the day.
Right.
Okay. Yes.
So, you would have an off-shell. You could have an off-shell line if you were calculating like a form factor.
Right.
But of course, at the end of the day, if you want real physics, everything's on shell.
Everything's on shell. Yes. Yeah. So just think about it for the nuclear physicist point of view. So I dumped on a bunch of people who make these things, but they have a tough problem. They've got 100 nucleons or so sitting in off shell in a potential. You don't have a whole lot of control over all of that. You think you're off shell. Nucleons on shell, but the constituents look like they're off shell. And so you make some approximation there. You say, well, I'm going to use some wave functions, and I'm going to put a potential inspired by field theory in between. And if I do the different approximations, I get slightly different answers. Well, it's tough to do that right. You can't really have this external nucleon and then decompose it to its external parts and treat the off-shellness properly, and so it's a tough problem. And if you do you start with, let's say, pseudo-vector, pseudo-scalar, you do get different answers. But that's because you've got an approximation there. It's not that one is right and one is wrong. And that only became clear when you could start doing 2 nucleons, 3 nucleons in bound states using effective field theories, where you can just you can do a well-defined calculation from start to finish. So that's from the other side. That's why people were misled into this. But nevertheless, it's worth staying away from that type of argument. Okay. Anybody else on that? Hog's theorem is a bit of magic, you know. If you do it a few times, you start realizing that it's going to work. But it sure doesn't look like there when I make this transition from, you know, a nice renormalizable field theory to this non-renormalizable looking one with the d mu u daggers around. Doesn't seem like every matrix element in the whole theory is going to have to work out, but it does. You know, there's you know, infinite number of matrix elements you can take. They're all going to work out.
So as long as it agrees to linear order,
As long as it agrees to linear order. So those are the conditions. Yes. Yeah, isn't it? It's neat. And doing it a few times, it works. There's another, you know, the handout that I gave you from Weinberg gives you yet another representation. It's the square root representation. So in that you see, historically, there was this U representation that we have here, this exponential one, wasn't the first one that was developed. It was the square root representation, basically, that Weinberg mentions in that. And in our book, we also show the equivalence by Hog's theorem of that guy. Anyway. Okay, anything else? Yep, all right, good.